So now we will move to the fourth presentation, and it will be about traffic forecasting on new roads unseen in the training data using spatial contrastive pre-training. And the presentation will be given by Ariane Prabhu, and the authors of the co-authors of the work are Wei Xiao, Lao Xu, Piotr Konius, and Flora Salim. And it's a journal track paper.
Oh. Okay, and I use this. Yeah. Okay. Hello. Good afternoon, everyone. My name is Ariane Prabowo, and covered by the thing is my co-authors. There you go. Hao Wei Xiao, Peter Cornelius, and Professor Farah Salim, who is here with us right now. And this is supported by many organizations in many different different shape and form. So yeah, the title starts with traffic forecasting. So let's talk a little bit about what is very briefly what is traffic forecasting. So lots of people in my posters ask about the sensors, so that's why I take a picture of the sensors, and this is exactly what the sensors looks like. It looks like some repairs happening on the ground, but what is actually happening, these are like induction loop detectors. This is a loop of wire, and when something magnetic is traveling over it, it will induce an electromagnetic current that can be detected by the sensors. So these are the sensors. What it can do is it can count number of vehicles that pass, and it can also measure the speed. And some more modern ones can do much more better things, but for our purposes, this is what they do, right? And so if you can see what happened is, if let's say this is measuring the speed of everything that passed, and we bin it for every like 5 minutes, what we get is a time series. We have a time series for every single detector like this, right? And our task of traffic forecasting on a single sensor is to, given the past usually 1 hour of traffic, let's forecast what is the next 1 hour of traffic. However, we don't do it on a single sensor. We do it on a we do it on a bigger traffic network. This is an example of one of the dataset, very popular in San Francisco. Every single dot will correspond to a single sensor like that, and every single dot will correspond a single time series. So we can formulate this as a multivariate time series problem. Yeah. So in a nutshell, our paper is about this. What if we have a new roads, or what if we install a new sensor on a new road that have very little data before? How do we do that? And our solution, just very quickly, is to come up with a new paradigm. And the idea is we are going to use contrastive learning in order to learn the behavior of the new sensors. The behavior on a new sensor using very minimal data set on inference time. So no more training happening, no more backpropagation happening, just on inference time. And so I'm going to start with the related works. Traffic forecasting are getting very popular. If you do the lit review, the number of papers grow more and more every year. I wouldn't be surprised if it's in the hundreds right now, every year. However, the topic is getting very saturated, right? The improvement becomes very small, very marginal, very close to be, I personally think it's getting very close to solved, because the performance is getting very good. But unfortunately, the performance is just very small. It's very exciting for us in the machine learning community, but it's actually not very exciting for actual traffic planners, managers, and engineers anymore. One of my favorite paper title in the literature, I'm not the only one who noticed this. Some other people might have, and one of them is this, who who wrote this paper, deep learning for road traffic forecasting, does it make a difference? And it doesn't just bash on our topic. They actually give lots of constructive feedback on where should the topic go in the future. So yeah, but otherwise, if we don't do something else, this will turn. I think this will turn merely as an intellectual exercise, which is a shame. I hope not. I hope it becomes more useful and more practical, and while still being intellectually very interesting. The other issue with the related works is that not only the topic is getting saturated, the data sets that is very commonly used are artificially small. These are the data sets, top 3 data sets that nearly everyone's using. As we can see, it only have like a few hundred nodes, right? 207, 225, and 228 nodes. Whereas the biggest that everyone has ever done on traffic forecasting, to my knowledge, is this one with 11,000s. So if you notice, it has the same thing, PAMs and PAMs. And what they do is what people do is people take a subset of the full PAMs data set, and then just run on that. Whereas this full PAMs data set is the entire California network. Yeah. And so to the rest of my knowledge, I'm the second person who try to solve the scaling, to address the scaling issue to this big entire network. Yep. So that is the paper. I like that people. I like those people. However, scaling is not trivial, right? Unfortunately, many prior works, and including many works that we have seen this week, they focus on like node embedding, positional embedding, and even one of the best paper this morning talks about the positional embedding time series, right? So yeah, I also find node embedding to be very effective. And just to quickly answer, but why is node embedding so effective? In the case of traffic, maybe different from something else, but in the case of traffic, one classical way is to model traffic as a fluid, right? So that means we will use things like PDE, right? And this ties back to today's keynote by Michael Bronstein talking about PIN, physics-inspired neural network, right? The PDE explicitly, if you think about it as equation, or as like in this case like a neural network, like the GNN that we're using, the models, is symmetric across traffic network, right? Wherever the Navier-Stokes equation, for example, for fluid, right, doesn't matter if we do it in the sea, in the Atlantic Sea, in the Pacific Ocean, for a cup in our water, the Navier-Stokes equations still apply, right? So it's symmetric regardless of location, and that's the same part here, right? However, in the perspective of PDE, we have boundary conditions, and that's what I think the node embedding is happening here. The node embedding is acting as a boundary conditions of this that breaks the symmetry, that breaks the spatial symmetry, and that is why I think node embedding is very effective. And this is also and I also found this based on our prior work showing that if the boundary condition is not symmetric, that means it should be different at every single place. And this is one of my prior work that does it. It does it by measuring by comparing. This is called a fundamental diagram, and it compares the speed and the average density. So the idea is if the density is very low, everyone's traveling at maximum speed. As density increase, the speed goes down, and the blue line goes up and down according to peak hour and quiet hours, right? And the idea is every single sensors have very different fundamental diagram because their boundary condition is unique, because they're the boundary condition, right? And so yeah, so node embedding is important, right? And so okay. And so the other question, right, about scaling, right, not only about the node embedding, but also about the edges. Many prior works, as explained during the keynote this morning, says that graph wiring is important, and it's also true. It is also true in traffic. Usually in traffic, people don't call it graph wiring. they call it adaptive agency matrix. But because everyone's doing with small graph of like few hundred nodes, what everyone's doing, the method that people use have very bad scaling issue. Usually the method that people use have the complexity of n square. So so scaling has many issues. One with node embedding and one is with graph rewiring. And yeah, and so I guess I should add this. So if node embedding is very important, then when we have new nodes that we have never seen before, then it's a big question: how can we learn the node embedding of a new nodes of a new sensor? Yeah, so the data sets are artificially small, scaling is an issue, and separately, contrastive learning has been very popular everywhere else, especially in CV, computer vision. However, it's struggling to find popularity in traffic forecasting. Yeah, and I think our work is the second or third work that introduced contrastive learning into traffic forecasting. And finally, one prior work. There's only one prior works funds. This one funds that try to solve unseen roads problem. However, they are context-driven instead of data-driven. So you have to know a lot about the road, like for example, like the geometry. I actually met the first author this morning. I'm sure you can. I'm not sure if he's. I don't think he's here, but like you can find him somewhere around this conference. I saw him earlier today. So just wrapping up the related works. So the research gap is that classical traffic forecasting is like close to solve. So it's time for us to move on to a new harder task, which is forecasting on unseen roads. And also people have found difficulty in implementing contrastive learning traffic, and we are the first few who successfully done this. And finally, there's a scaling issue with a small data set. And what we do is using this new roads paradigm. What if we only train on 1% of the network, 1% of the sensor, and then we treat the other 99% as new roads that the models have ever seen. Right. So that is our strategy to scale to 10,000 networks efficiently and effectively. Finally, I hope I convince you that the gap is real. And this is an important issue. Let's go with the methods. So just a quick glance. We pre-train a spatial encoder using SCPT. And the idea is, yeah, so we train a spatial encoder. So during inference time, we use this, we can infer the node embedding, the spatial embedding of the new roads from minimal data using this spatial encoder. So because this is different than normal forecasting, we need to have a new split, and the new split basically means we just have to make sure that the nodes, some of the nodes are unseen in the training data. That's yeah, we have to split the data in a new way. And this is our architecture. This is very similar with Simpler in computer vision. However, yeah. And very quickly, this is the original Simpler from computer vision, and the idea is that you have the same pictures and you augment it in two different ways, and then you put through some network, an encoder, CNN encoder, and then the idea is and then you get a representation, the representation learning, and you want to make sure that the representation from the same picture, it should be similar, it should attract. And a representation from a different picture should repel. Right? That's the idea of Simpler. And however, we cannot use augmentation in traffic forecasting, right? Because for example, in image you can increase the brightness. That makes sense. However, if we increase the speed by 10, that means everyone is breaking the speed limits. It means completely different thing, right? Whereas a picture of a chair with slightly increased brightness is still a chair, right? So instead of using augmentation, what we do is we use sampling instead. We use sampling instead of augmentation. And as you can see, this has a very similar a very similar idea with SimClear. And so after the most valuable part over here is the encoders that we trained. Once we got the encoder, we can just use any other traffic forecasting backbone out there. For this paper, we picked GraphWaveNet because it's one of the most popular one. But you can use with anything else that implement node embedding. And so so this is our architecture agnostic, and this is how we integrate our encoder with the existing backbone. And so let's get to the most important part, the results. So in this 3 common data set, testing on 20% of the routes that the models have never seen, the improvement rate ranges from 3% to 12%. To 13%, depending on the data set and depending on the metrics. So more importantly, the blue line is we do replication. The blue line 10 times replication. The blue line is the baseline, and the orange line is ours. And what it shows is that if we forecast for a longer duration, for example 1 hour, the performance gap is better. So we perform better the longer the forecasting horizon. And finally, the scaling issue, right? As we said before, the dataset is artificially small. One naive way to do it is let's just use one large model. There are many issues with that. It's inefficient. There are more technical overhead. You have to use distributed data parallel, more complex methods, more complex engineering methods. And then there's also the scaling issue that we discussed before. Right. And one other person tried this by using graph partitioning. And what we do is let's train only on small 1% of the roads and treat the other 99% as new roads. And the result is this. So I know this table is a little bit hard to read, but this is the graph partition method. It took basically 8 days, just shy of 8 days, and they get a median MAE of 2. Whereas we get a median MAE of 3.2, which is lower, but it only takes us 22 hours. 22 minutes of training time, right? So we train only on 111 nodes, only on 1% of the nodes. So what this means is that we get a favorable trade-off between error and speed. You don't have to use 1%. If you want more accuracy, you can go to 10%, and so you have this trade-off between if you want how much accuracy that you want. I hope this will become more useful for the actual engineers, traffic engineers, machine learning engineers implementing this. And in conclusion, we are proposing a new task, and that is forecasting on new roads, unseen roads. And I hope this is an interesting task in many ways, right? On one hand, from graph machine learning and from geometric deep learning perspective, this is not just a normal graph attribution. This is not just a normal graph node prediction, but it's more interesting. From a physics-inspired neural network perspective, I hope this is also interesting because there's an underlying PDE below that is not, it's also interesting obviously from the mobility spatial-temporal time series perspective, and also from the applied data science for the traffic people. Our method SCPT is just the first data-driven. It's just the first step to do this task. I'm sure many of you can do better than this. This is just the first try. There are so many ways to improve on our model. And finally, this method will have also the scale efficiency and as I said before, the trade-off for the engineers. And yeah, that's my talk. Thank you very much. If you have any question, and this is the link to the GitHub. Yeah. And the code is, and I already upload all the codes. Yeah, you can.
Yes, thank you for the talk.
Thank you.
It's very interesting. I just have one question regarding to the different structures of the sensor network, because as you mentioned in traffic forecasting domain, there are few working on scalable graph networks, scalable graph structures. But in other community, like in other research programs such as air quality forecasting and also graph neural networks, there are a lot of work on expandable graph neural network. So have you compared with that kind of method?
No, I have not, and I think that's a real research gap that someone should use.
Okay, thank you. Because regarding to this question, I just want to know, for instance, you mentioned in the inference step, you can have the prediction for unseen route. So this prediction is based on the like the spatial locations or the connectivity in the graph network.
So that is the next step that I have in mind. For right now, we just use it for the spatial. It's actually a little bit of both. We use it to infer the node embedding, and then we use the node embedding to infer the adjacency as well. Yeah. But it's not a very but the way we do it is just the way other people have been doing adaptive adjacency. Yeah.
Okay, got it.
Thank you. Yeah. So this is just to answer that question. This is the module that we talk about, and then we perform ablation on this, and then it shows the importance. Yeah. Thank you.
I think you said that in traffic forecasting, there is
Yes.
no challenge because we have some good performances.
Yep.
But I think the challenge is on forecasting the traffic when the condition of traffic are not common.
Yes.
I think this could be a challenge.
Yeah.
Because here but other work also, we estimate the performance in the whole performance of the traffic prediction. But if we can focus on some particular condition of traffic, this could be a challenge, I think, in forecasting.
Yes, I completely agree. We should, there are so many different new challenges, and we should start exploring them instead of just the normal, typical performance. Completely agree, 100%.
So thank you again for your interest.
Well, thank you very much for listening.